All right, today we're going to look at lesson 4.3, characteristics of linear functions. All right, we're looking at task 1 if you want to follow along. All right, it says identify increasing and decreasing functions. All right, a function is increasing on the interval if the output of the function increases or stays the same as the input increases. A function is decreasing on the interval if the output or the function decreases or stays the same as the input increases. All right, so this is mathematical terminology as a way to say a function is increasing if it's going up from left to right, and the function is decreasing if it's going down from left to right. So if you just remember, we write from left to right. Your sentences, you read from left to right. So on a graph, if it goes up from left to right, it's increasing. If it goes down, it's decreasing. That's simple. All right, you can determine if a function is increasing or decreasing by analyzing the input or output values. Consider what happens when you increase the input x of a linear function by 1 unit. All right, f of x equals mx plus b, so this is our slope-intercept form that we looked at before, and we're going to increase it by 1 unit. So all they're going to do is, instead of x, we're going to increase it by 1, so x plus 1. So what they're going to do is take the x over here and do the same thing, x plus 1. So we're just substituting x plus 1 in place of x. All right, then you're going to distribute. Take the m times x, mx, and m times 1. M times 1 is just m. All right, then you can use commutative property to just rearrange these values. So if I switch m and b, b plus m is the same thing. So all we're doing is rewriting it. Now, why are we doing that? Because mx plus b, you look right here, mx plus b, we know that equals f of x. So they're going to replace the mx plus b as f of x. And then, of course, we still have the plus m. All right, so that's just kind of a more complicated way of saying, what does the m represent? The m represents your slope. All right, it says complete the following sentences. The value of m must be blank if the function is to increase as you move from f of x to f of x plus 1. So the slope must be positive if it's going to increase. The value of m must blank if the function is to decrease. So the slope must be negative if it's going to decrease. Positive slope increases, negative slope decreases. All right, we're going to move on to task 2. If you want to pause the video and meet me back here in just a second at task 2. All right, task 2 is talking about determining the end behavior. So this is another characteristic of a linear function, and really any type of function. We'll be looking at end behavior for lots of different functions, but we're going to start with linear. All right, the end behavior of a function f describes the trend in the output values f of x as the input value x either increases without bound or decreases without bound. The notation f with the arrow plus infinity is read x approaches positive infinity. So you'll hear me say this a lot, as x approaches positive infinity, and I'll write it just like this. And the notation x with the arrow negative infinity is read x approaches negative infinity. As x approaches positive or negative infinity, f of x, which is your y value, can approach positive infinity or negative infinity as well. Okay, so what does this mean basically? Well, when you're looking at a graph, you have x's and you have y's. So the end behavior is determined by what happens to the graph as x goes negative and x goes positive. So when x goes down, when x is going towards negative infinity, in this graph, it's going down as well. So when it goes to the left, you're going to negative x's. So as x decreases, my y's are decreasing as well. Okay? So it says, what is the domain of f? So the first thing we want to determine is the domain. So x's go without bound in both directions with arrows, that means it's going to the left and right forever. So that would be all real numbers, which can be written negative infinity to positive infinity. That's another way to write all real numbers. All right, if the graph were extended to the left, what would the graph look like? Choose the words to complete the answer. All right, so if the graph were extended to the left, okay, the arrow is going to continue to go down. That means it's going to keep going down. So it says the output values, that's your y values, would decrease without bound along a straight line because it is a linear equation. All right, what is the end behavior as x approaches negative infinity? So this is still talking about the exact same thing as x goes to the left, because to the left is your negative x's. Choose the number or symbol to complete. So as x goes to the left, my y's are going down without bound as well. So that's going to be negative infinity, shows that my y values, or f of x, which is y, goes to negative infinity. All right, if the graph were extended to the right, what would the graph look like? All right, so if we extend the graph to the right, it's going to continue going up. So we see that our x's are going positive, and our y's will also be increasing. So they would be positive as well. So we can say if the graph is extended to the right, so the output values, that's my y values, or my output would increase without bound along a line. All right, what is the end behavior as x goes to infinity? Y goes to infinity as well. All right, how would the end behavior change if the function were defined as f of x equals negative 1/2 x minus 3? All right, very quickly. This has a negative slope. That means my line would go down from left to right. So if it's going down from left to right, as your x's go to the left, your y's would go up. So x to the left is my negative. It would go up. And as x goes positive, it's coming down. So it'd be negative infinity. So you're really just talking about the direction, what's happening for the end behavior there. All right. If you have any questions on this, please let me know. I would take good notes on this because you will need to know all of these symbols and terminology. Okay, looking at task 3 in lesson 4.3, characteristics of linear functions. And this time we're looking at identifying zeros. So a zero of a function f is any value of x such that f of x equals 0. So when y is 0, that's called a zero of the function. Later you'll find out that that's a solution of the equation. All right, so the graph and table represent a linear function. It's a straight line, so it's linear. So the graph and table both represent linear functions f and g respective. Okay, so here is f and here is g. All right, so it says complete each statement with the letter or number. So the 0 of f is the blank intercept of the graph. So the x-intercept of the graph, the 0 of f is equal to, all right, so it's over 1, but you got to be careful because look, there's negative 4, so it's going to be negative 2, negative 4. So that would actually be at negative 2. So you always have to look at the scale of the graph. All right, choose the word or number that best describes the statement. To find the 0 of g, look for a 0 in the second row because this is your y value. So there's your 0. So the 0 would be at 10, 0. So to find the 0 of g, look at the 0 in the second row of the table and then find the corresponding value. The 0 of g is equal to 10. All right, so choose the function to complete the statement. The function blank has the greater 0. All right, so does f or g have the greater 0? So this one says F has a 0 at -2 and G has a 0 of 10. So G has the greater 0. 10 is greater than -2. All right, if you have any questions, let me know.